Swayam Prabha. Digital India. Educated India.
So let's suppose that you have two beams of light which start out in phase. So the waveform for this beam of light looks like this. So we'll write it as A1 sine of k, let's write it as omega times t minus k times x. And for the second one, we will use some other amplitude. The amplitude doesn't matter, we're interested in the phase. Sine of omega t minus kx. Now the frequencies omega are the same, okay, because the light is sourced by the same, let's say the same source. However, these k's, which are related to the wavelengths of the light, could be different if the light travels with different speeds. For example, as light travels through different mediums, for example in glass, right, we know that the wavelength changes due to and this causes the phenomena of refraction. So the relationship between k and omega is of this form. Omega is v times k. So in general, if this light beam now travels with a speed v1 and this light beam travels with a speed v2, k1, which is this wave number over here, which is 2 pi by the wavelength, that would be related to omega as omega over v1. And similarly, k2, which is this wave number over here, would be 2 pi over whatever this new wavelength was, which would be omega over v2. Okay, and you can see that initially at time t is equal to 0, and let's assume that they start at x is equal to 0, they are completely in phase. That is, this phase and this phase are the same. However, after they travel some distance, okay, after I wait some amount of time and then I compare their phases, so the times are the same. So the only phase difference that they would pick up is due to the different path lengths that they would travel because they have different speeds. So if I compare them at the same time in the future, what I would see is that the first wave has picked up an extra phase, which would be k1 times the path length that it has covered, and k1 times the path length that is covered would be omega by v1 times L. And for the second wave, similarly, we can write down the phase that it picks up as k2 times L, which would be omega over v2 times L, assuming that they cover the same length, but they're just traveling at different speeds. So now the phase difference of the Michelson and Morley experiment can just be written as omega into L, 1 over v1 minus 1 over v2, where the first term is due to the phase difference picked up by the first wave, and the second term is due to the phase difference picked up by the second wave. So what this interference pattern would lead to would be things like this. You'd see bright spots, then dark spots, then bright spots, dark spots, bright spots, and dark spots, corresponding to constructive interference, where the phase difference was an integer multiple of 2 pi, and dark spots, which would correspond to where the phase difference was an odd multiple of pi. Okay, and this phase difference was purely speculated to arise from the fact that the speed of light must be different in different directions since we're drifting with respect to the ether. Now, in reality, when performing this experiment, the thing to keep in mind is that it's not really always possible to arrange for the two path lengths to be exactly the same, right? Because you need to do this very precisely. So if you call this length L2 and this length L1, it's not possible to arrange for them to be exactly the same. So you will get an interference pattern even if the velocities v1 and v2 were the same, just because of the fact that your experimental setup doesn't allow you to set equal path lengths. Okay. However, what should happen is that as you rotate the apparatus, so as I imagine making a rotation of this, the path lengths continue to stay the same, but the velocities or the speeds v1 and v2 will change because now the light is moving in a different direction relative to the velocity of the Earth in the ether. Okay, so as you rotate the apparatus, what should happen is that this interference pattern that you saw should shift either to the right or to the left. So the fringes, the bright and dark spots, will shift either to the right or left as you rotate the apparatus because of the fact that the speeds v1 and v2 will change as you rotate the apparatus. So the goal of the Michelson and Morley experiment was to look for this fringe shift. So the fringe shift goal was to look for the fringe shift as a sign of ether drift. Now, Michelson and Morley did this experiment in 1887. Their apparatus was very simple and set up on a tabletop. And they tried to look for the shift in this interference pattern. And they found something surprising. No matter how they rotated their experiment, there was no shift in the interference pattern. When they looked at it at different times of the year, they could again find no shift in the interference pattern. This result was quite stunning because no one expected this at all. People speculated on all kinds of other ideas. For example, there was a theory of so-called ether drag, that as the Earth was moving through this ether, it was dragging the ether along with it. And so therefore, we would be at rest with respect to the ether, and it would not be possible to detect our motion relative to the ether. However, since the ether is the medium in which these electromagnetic waves propagate with a fixed speed, or that was what was speculated at the time, you would also see distant stars where the light from these distant stars would not be affected by the Earth's drag, because the Earth's drag would only act on the nearby ether. The light from those distant stars should experience an aberration. Okay, there would be a discrepancy in their positions due to the drag of the ether. No such effect or aberration was seen So such alternative theories to explain the null result of the Michelson-Morley experiment also were contradicted by different experiments. This result was extremely puzzling to the physics community. On the one hand, you expected that Maxwell's equations tell you that there's a preferred rest frame in which the speed of light is c. On the other, Galilean relativity tells you that when you are moving with respect to this preferred rest frame, you should measure different velocities for light or different speeds for light in different directions. Yet, we could not detect the effect of these different speeds of light in different directions. How could this be? The physics community had run into paradox. Let's try to clearly elucidate what that paradox is. Newton's laws appear to be consistent with the dictionary of Galilean relativity. Maxwell's equations appear to show an inconsistency with Galilean relativity. Firstly, because there was a constant c, which indicates that light has to travel at a fixed speed with respect to something, and we need to know what that something is. And it was speculated that this was because of ether, but the null result of the Michelson-Morley experiment told us that there appears to be no ether. Okay. So, what are the possibilities now that we could imagine to resolve this discrepancy? Well, the original possibility of reconciling Maxwell's equations with Newton's laws was to speculate that there's an ether and therefore there's a preferred rest frame, but this was ruled out by the null result of the Michelson-Morley experiment. A second possibility is maybe Maxwell's equations are just wrong. Okay, and maybe they have to be modified to correctly fit with the Galilean relativity principle. Or a third possibility is that maybe Galilean relativity is wrong, and there is a new relativity principle that describes how different observers translate their observations between each other. And this new relativity principle is consistent with Maxwell's equations. Now, if Galilean relativity was wrong, that would also imply that Newton's laws are not correct. Okay, so this would also imply Newton's laws are incorrect or need to be modified, because they fit quite well with Galilean relativity, or they appear to. So the question is, if you take this third approach, is there perhaps a new relativity principle that is consistent with Maxwell's equations and modifies the form of Newton's laws so as to also be consistent with this new relativity principle. And therefore, the original form of Newton's laws, which is consistent with Galilean relativity, is wrong. Although it was hard to imagine at the time how this could even be possible. It wasn't until the year 1905 that a young patent officer in Bern in Switzerland named Albert Einstein, who was all of 26 years old, began to think deeply about the idea of the Michelson-Morley experiment and came up with the new relativity principle, which was dubbed special relativity. We will see Einstein's reasoning and we will follow it to understand exactly how he came up with this new relativity principle and the simplicity of thinking that led to it. If you're going to abandon Newton's laws and treasured principles of Galilean relativity, you need to know what ground you have to stand on. If you can't trust anything, where do you begin? And we will see that the genius of Einstein was to figure out what are the right principles, what are the right things, ingredients to begin with, to assume in the character of the physical law, from which he derived his new relativity principle. So Einstein tried to figure out what are just the bare minimal building blocks that he needed to characterize what different observers would see and what the nature of physical laws really was. And he made a few simple postulates. So let's write those down. These are the postulates of his new relativity principle called special relativity. So the first thing he did was to assume that there are still a class of observers in this new relativity principle whom he called inertial observers, or they inhabit what are called inertial reference frames. And his first postulate was that whatever the laws of physics, whether Newton's laws, Maxwell's laws, these laws of physics are the same in all inertial reference frames. Okay? That is, there are a class of observers who are in a state of constant relative motion to each other, and these observers should all see the same form of the physical laws. They might differ again in their descriptions of the physical laws, of various quantities like positions and times, but they will agree on the form of the physical law. Okay, that was a starting point. Then he took a second principle, and this was where he differed with what had come before from Newton's laws. He simply took it as a principle of nature that the speed of light c is a constant in all inertial reference frames. This would obviously explain the null result of the Michelson-Morley experiment, because if the speed of light c was the same for all inertial observers, we would not be able to detect any fringe shift in the Michelson-Morley experiment. Because no matter which direction you look, the speed of light was always going to be c, and therefore the phase difference between two arms of an interferometer would not change if the light was traveling in different directions. Now, in addition to these two postulates, there are a few unstated postulates which he invokes at a later time. So these are the so-called unstated postulates of special relativity. But these are also very simple, which is to assume, one, that there is an origin independence in space and time. That is, there's no preferred position in space and no preferred position in time. Okay, so this is called the principle of homogeneity. All points in space in a given reference frame appear to be equivalent. Right? There's no difference between here and there, or between now and in the future. The form of the physical law stays the same. There's no preferred point in space and there's no preferred point in time. So this is called the principle of homogeneity. And the second unstated postulate is to assume isotropy, which means if I rotate my coordinate axis in trying to describe my system, again, I should see no change in the character of the physical law. Okay? That is, my physical law doesn't care about which direction I refer to as the x-axis, the y-axis, and the z-axis. Even if I rotate these axes so that perhaps the x-axis is pointing here, the y-axis is still pointing this way into the paper, and the z-axis is pointing this way. Even under this rotation, the physical law would take exactly the same form. Okay, so homogeneity has to do with translations in space and time. Okay, this is where you're talking about observers who are not moving with respect to each other, but are just located, have different choices of their origins in space and time. And isotropy has to do with observers who have axes which are rotated with respect to each other. And all such observers should again measure the same form of the physical law. And he simply began with these four principles, no other assumptions. And he used these to derive a new principle of relativity. So let's summarize these principles again. One is the principle that there are a class of observers who inhabit inertial reference frames, and the laws of physics must appear to be the same for all these observers. Second, the speed of light c is a constant in all these inertial reference frames. Third is the principle of spatial homogeneity, or the fact that no point in space and no point in time is special. And the fourth principle is the principle of isotropy, which is there's no preferred direction in space, so there's a rotational symmetry of the laws of physics. So let's begin by thinking about this particular example. So imagine that you're looking top down at a railway platform, and we have an observer O who's standing on the platform at rest. So this is observer Om Prakash, and we're in the frame of the platform, so we're at rest with respect to this platform. There are a bunch of different observers, or his friends, standing 1 meter away. Okay, so each one is 1 meter stick away from the other, and they're all denoted in different colors here so that you can clearly see who is who. And each of them, you can clearly see they have these dials, which are their wristwatches. So you can see the time on their clocks, and you can see that all their wristwatches are synchronized. So they can all tell the time, and the time is shown here in red as -8 seconds. Okay, and now they're waiting for a train, and this is the train that's passing them, and this is a bunch of people in the trains, and Om Prakash's evil twin, O Prime Prakash, shown here with this pink dot, is sitting on this train with a bunch of his friends. And now we're going to see what happens as these trains pass each other. So it's going to take a while. These trains are moving slowly. But you can see that it's in a state of uniform motion. And now let's look at this instant of time where Om Prakash and O prime Prakash just pass each other. So O prime Prakash is just passing Om Prakash. So if Om Prakash looks into the train, he comes face to face with his evil twin. Now let's assume that at time t is equal to 0, when O Prakash and O prime Prakash pass each other, there is a lightning strike that occurs simultaneously at two different points, A and B. Okay, so Om Prakash's friend over here, who is a distance of 1, 2, 3, 4 meters away to the left, and friend B, who's at a distance of 1, 2, 3, 4 meters to the right. So Om Prakash is sitting at the midpoint between these two friends. Both these friends experience a lightning strike. And now we'll assume that this train is very close to the platform. So the corresponding observer on the train, who's sitting over here, would also see this lightning strike at the same instant of time that A sees it. And the corresponding observer over here would also see the same lightning strike that observer B sees. Okay,